right, let's talk about reactive programming. This is something that's been exciting for me. I've been speaking about this for a few years. And I'm going to say within the last year or so, I'm seeing a really good surgence of different libraries and frameworks becoming reactive as well. So what I used to think as something to explore suddenly is something that we have to really start working with. So this is no longer a nice idea to learn about. It's something, it's very practical that we can actually begin to use. So is this something which is really totally new? Well, I've learned that we work in a field where about every 10 years we'll give a new name for what we already do and get really excited about it. And this time around, things like reactive programming, microservices, and a lot of other things we talk about. But this is not really new. In a way, I would say reactive programming is kind of like extreme programming. If you think about extreme programming didn't have anything new, and yet what was really new about it was the emphasis it had on the 12 practices and principles. In a similar way, reactive programming brings 4 things to the forefront with a great emphasis. We'll talk about what those 4 things are in just a little bit. But what is the reason for this renewed interest and urgency? What's causing that? Well, there are a few reasons, because we live in a world suddenly different from the world we lived in only about 15 years ago. It's strange that we could see such a drastic change in a short amount of time, but that's very rewarding as well. One of them is big data. We're dealing with high volume, high frequency data. And thanks to 2 things that has happened, the change in the internet technology or the availability of it, and also the multi-core processors have given us the ability to do that. We are dealing with internet-enabled devices. The biggest geek I personally know is my son. And the other day I patted him and several devices fell off him. I don't even know how many he carries. And we're talking about people carrying multiple devices. I'm almost nostalgic when I say it. I remember the days when I used to wake up, when the coffee pot was brewing coffee, I would turn on my modem, and it would wish and reconnect and connect and reconnect. Then I can call my friends and ask them what baud rate they are getting. Those days are long gone. We are carrying devices with us constantly. And I'm saying forget about wearable watches. We're beyond that. We're talking about earrings, nose rings, and tongue rings, all internet enabled, constantly communicating data. And we're not far away from days where a doctor could call a patient and say, I'm monitoring your health here remotely, and you need to sit down. Maybe there's a higher blood pressure, and they could be monitoring. We could be looking at devices. We could be looking at airplanes in flight, and we could be gathering data. And of course, the usage patterns are changing very drastically. One of the other things that has really changed is, about a decade or earlier ago, organizations made applications available to their employees and made their employees available to the users. Those employees are called as captive users, meaning nobody cares what they think about. On the other hand, when you make the applications available to the real world users, you have a bigger scale, but you also have a bigger demand and expectation as well. So to meet some of these changes, we need to rethink about how we develop applications. So reactive programming was introduced quite a long time ago, but I want to say in 2 phases. One is Eric Meyer introduced reactive programming as part of his work in Microsoft Research. And I work with Microsoft Technologies. I work with people who do technology applications in Microsoft Technology. But I've noticed one thing quite different between the people using Microsoft Technology predominantly and people using Java and JavaScript. When you go to the Microsoft world, when you give a solution to people, these are fantastic people. They will take the solution and they'll quietly sit and work and produce value and give you results. The Java people and JavaScript people are very different. You give them a solution, they will run to create 20,000 frameworks around it. And that's when this really became popular, when the Java world and JavaScript world discovered this, even though this has been around in .NET for a while. But in practical terms, reactive programming is something even older. It's been around since the beginning of computer programs available. One of the best known reactive applications you probably can think of is Microsoft Excel. Microsoft Excel, you can change a column and immediately any column that depends on it changes. And that is an example of being reactive. You could just modify a column and see all these changes ripple through immediately is pretty phenomenal. That's a reactive nature of it. I discovered reactive programs in a slightly different way, and that was a like aha moment for me. That was through Google Docs. I travel almost constantly. So one of the ways I keep in touch with my family is through electronic medium. I share a Google Doc, a couple of Google Docs with my wife. Well, that's no big deal, but I discovered something really fantastic one day. I was in a remote part of the world, and I get up in the morning, and I log on to Google Docs, and I found that I can see where she is logged in. I could find out the location of the cursor where she is editing. And knowing that, I've realized I could modify that exact location where she is editing. With this ability, reactive programming is awesome because you could be thousands of miles away and still find a way to annoy your spouse. And this is just amazing technology for me. And until she says, get out of my document now. So this is really ability for you to share the document with somebody who is thousands of miles away and to collaborate is reactiveness. Remember the day you discovered infinite scrolling. You've been using this app for a while. It's a little slow and sluggish, but you went to the app and it gave the result right away. You're like, wow, that was pretty fast. Why so? Was it a better connection? Did they redo the app? And then you scroll up, and your brain is just catching the fact there's no bottom. And then you realize, before you could blink your eyes, it fills up with data. And then, of course, reactively, it's able to pull the data as you're viewing something. It can be fetching more data and filling the scrolls. That's pretty amazing how that can happen. So what is it really? Well, the very first thing about reactive programming is it emphasizes message-driven architecture and message-driven systems. None of these is new, but it really brings those four things together. Well, we've been using message system applications for a while. I'm going to say using a centralized database and the distributed transactions is so 20th century. It doesn't make sense to create applications of today where we want these disparate systems to communicate with each other using databases, which are central locations. So we really want to be thinking about messaging between applications. And so reactive programming greatly emphasizes messaging. There are different solutions for messaging. Vertex is one example, but just one way to do it. There are other communication tools and techniques also you could use for messaging. But then the next thing to discover is we live in a world where the scale depends on the application you are building. You could be a little application where you don't really care so much about scale. You could be an application where you can't predict what the scale is. Who knows what the scale is in certain applications? I was talking to a client of mine, and I asked them the question, how many users do you typically have? And they said, well, typically we have about 200 users using the system. I was a little shocked because they're a multi-billion-dollar company, only 200 users. And they said, well, you said typically. Well, typically 200 people use the app, but on a 2-day period, about 50 million people use it. Well, how do you scale from 100 people using your application to millions of people using it over a short period of time? Well, we've learned the lessons of this in the cloud computing world. Elasticity is very easy and approachable. We could configure systems to come to life, either dynamically when the demand goes up, or on a particular given time period. And then when the demand goes down, those systems can be decommissioned, so we can pay only as we use it, and we're not paying for anything, we're not using it. Also, it becomes really powerful to be able to deploy these machines dynamically and configure them dynamically as well. So elastic computing is something we have learned a great deal. Responsiveness is something we need to be also thinking about quite a bit. It is really not about how fast you can give the result, but how responsive can you be in giving the result. If you are going to come back and give me all the results, but in a delayed mode, we live in a world of instant gratification. We're not going to wait on an application forever to respond. That's applications that don't respond quickly are the applications that are going to lose the users. And you want to really be able to respond very quickly. For example, you may walk into a store on a Saturday morning, and you watch this a clerk busy with another customer. So what do you normally do? You probably look around for a few seconds. You look at the wall, you look at the ceiling, you look at the floor, and then you realize there's been a minute and there's no response, and you leave. On the other hand, you walk into the store, the clerk who is busy makes an eye contact and says, I'll be with you shortly. You probably waited for a good 10 minutes. Why is that? Because you felt you are important even though you know you're not. The point really is that when there is responsiveness, you really have the loyalty, and that's one of the reasons. So this is kind of what infinite scroll does, for example. It gives you a response very quickly and then can come back and give you more. But think about this for a second. What if you can take this responsiveness and you can do this throughout the layers of your application? Think about pagination. Think about infinite scrolling. How do we implement that in a web application today? You might take the data request, you send it to the server says, oh, I have given you this much data, I'm going to go to the database and get you some more data and give it to you. Well, that's a lot of burden on us. What if you can take that conversational thread from the front end all the way to the database, where when you make a request to the database sends you part of the data, and then it can keep streaming back data to you. This is not an idea or a theory. This actually is true today. A lot of databases have started implementing this already. So you can go to databases, and rather than getting a record set, you can get a reactive observable, and they can start streaming data to you. So you can take this reactiveness from the front end all the way to the back end into one single conversational thread. That becomes a lot easier. But another thing we have to be very careful about is resilience. We cannot ignore the performance of applications and keep our focus only on speed of execution and scale, but on actually the fact that it actually works, and if it's going to fail, that it fails gracefully. Resilience is another deciding factor for applications to be used in the industry. If I ask you how many applications you have on your smart devices, you're probably going to tell me you got hundreds of apps on your smart devices. But if I ask you how many do you actually use, you probably use a dozen applications. What about the other applications you don't use? Most of them are pure crap. In fact, you're so angry at them, you left them there to die. They don't even deserve your touch to kill them. And that's the whole point, is when applications are not very resilient, you don't continue to use them. I'll share with you a story, kind of a sad story related to this. I was speaking at a conference when a gentleman came up to me and he said, hey, I want to let you know, I have a story to tell, he said. I took one of your courses, a distributed object computing course at the university back in 1998. I said, oh my gosh, I remember teaching that course in the 90s. He said, well, I want to tell you what happened in that course. He goes on to say, he was in the class and he was, it's a distributed object computing course. So you obviously have to write code where you communicate across different processors. And apparently, he said, there was a final demo of the project. And he was doing the final demo. And right in the middle of the demo, I had walked up to his machine, disconnected the internet cable, and went back and I said, continue. And his program failed, and he failed the project. And when he said this, I said, I'm really sorry to hear this, but why do you want to come to me and tell me such a sad story that you failed in my course? He said, because there is a good ending to this. I don't understand how there could be a good ending when you failed my course. He said, you see, that's the last day I ever programmed that way. He went on to say that he programs for resilience now and doesn't program the happy path alone. His narration was, he said, now at work when I code, when I'm in front of my computer, when I take a project to implement, on my wall in front of me, he said, I have a picture of evil Venkat. And I look at this picture every day and I code. I don't think we want to have a picture of evil Venkat to be resilient in our programming, but it really emphasizes that we cannot ignore resilience. We have to really program for it. Okay, so we want to achieve these goals, but if resilience and responsiveness is very important, can't we just use multi-threading? Well, what do you do with multi-threading? You start a thread, and then the fun starts. What happens after that? When you have shared mutability, it becomes really hard to deal with. What if you create multiple threads, and multiple threads begin to fail at the same time? How do you get the response from these threads? Not very easy to work with. Well, can't we just use futures? What do you do when you have futures? You call a method. The method immediately gives you back a future. And the method is running in another thread. And what do you say? You say, hey, this is great, but I want the result. So what do you do to get the result? You call the futures.get. What happens when you call get? Your thread gets blocked. That's called the future is very bleak. It doesn't really help at all because you're not going to utilize your thread very effectively by calling a get method. So that doesn't work. Oh, there's a much better way to do this. We can all use callbacks. If you think callback is a good idea, I've got a suggestion for you. Just sneak up quietly behind a JavaScript programmer and utter the word callback and watch them begin to cry unconsolably because they know how terrible callbacks are. Callbacks don't compose very well. They're very difficult to work with. You got to register in a particular sequence. Really no good way to handle error versus data. So it doesn't answer really good questions. In fact, the JavaScript world has moved away from callbacks to promises and such. And so what do we do about this? Well, before we talk about it, let's step back and talk about this a little bit. What we want is resilience. What we want is responsiveness. What we want is scale. And what we want is to be able to build applications in a way that we can maintain them. Well, there's something we need to really think about. There's the saying. They say, what do you do when you are chased by a bear? And the general recommendation is not that you have to run really fast. The rule of being chased by a bear is you got to run faster than the person behind you. And that is exactly the whole thing we need to really think about. And so it's not about running really fast. And this is where the efficiency really comes in. So efficiency is attained not by doing tasks faster, but by avoiding tasks that shouldn't be done in the first place. So this is essentially about laziness when it comes to programming. So both in life and in programming, laziness is the ultimate benefit. So in other words, laziness has the ultimate benefit. In other words, if you postpone executing something, you get to a point where maybe you don't have to execute it at all. That is the most efficient. Not doing something is the most efficient way to do it. And of course, when you do have to do it, by postponing it, you have another benefit. You can do what is imminent and important now, and you can do what is imminent and important later at a later time. So you can be efficient by being lazy. So I was struggling with this, and I was trying to understand, how does this all fit together? Because I like to have a clear path of transition in my mind. I'm not very good at dealing with isolated ideas. I like to have connectivity between ideas in my mind. I want to be able to say, this is this particular paradigm, and here's how this is different. As I was struggling with it, a little light bulb went in my head, and that realization was that reactive programming is a nice next logical step to functional programming. Because in functional programming, we deal with function composition and lazy evaluation already. That's basically what we have on our hands. So we have function composition and lazy evaluation in that we can nicely start transforming data, and we can also apply those transformations lazily at a later time when we want to. Well, reactive programming takes these ideas of function composition, lazy evaluation, and runs with it. So I see that reactive programming ideas are not disjoint from functional programming, but more of an extension to functional programming. And that I see as a very nice way to relate these two ideas together. So in that regard, in functional programming, there is one little idea we need to keep in mind. Functional programming is this idea about composition of functions. We talk about stream-based programming, for example. So you have a data that flows through, and you go from upstream to downstream. Well, unfortunately, exception handling is a terrible thing that doesn't work with these ideas. The idea of exception handling is so imperative in nature. What do you do in imperative style of programming, where you write your loops, you control the primitive obsession, you have loops where you control the looping entirely? Well, you call a method, the method blows up, and you catch that with an exception. That works really well in imperative style of programming. But exceptions don't make any sense in a functional style of programming. Because in a functional style of programming, you flow through the stages of the pipeline, calling one and then transforming data and transforming data. When you're downstream and something goes wrong, you don't have the luxury of backtracking. So what you do is you continue downstream with the error and you deal with it in the end. So in other words, these two ideas are not orthogonal. These two ideas are conflicting with each other. And there's a difference between what's orthogonal and what's conflicting. What's orthogonal can live with each other. What's conflicting don't work with each other. So the functional style of programming and exception handling are conflicting. We can put them together. Well, this is where we handle errors very differently in reactive programming. In reactive programming, we respect failures. In fact, I would argue one of the worst things we did is calling exceptions as exceptions. We should have called them normal. Because something goes wrong, we feel surprised about it. There's nothing surprising. Life sucks sometimes. Code will fail sometime. And let's just better deal with it. And so it should be normal and not exception. Well, what if we treat failure with respect as something we do expect, and we start dealing with errors from the get-go? So rather than try to treat the errors as something different and strange, what if we treat error as yet another form of data? So in other words, in reactive programming, errors are treated as first-class citizens rather than something exceptional or different. So how does this all work? Well, before we talk about it, I want to step back and think about where we have been and maybe where we should be. So what have we been doing for the past about 15 to 20, maybe 25 years? We can summarize that as CRUD applications. A lot of applications we have built are CRUD applications. We create data, we read data, we update data, and occasionally delete data. At some point, we wake up in the morning and ask the question, is everything CRUD? Have we gone overboard with it? Maybe there are times when we are not dealing with CRUD apps. Maybe there are times when we will be dealing with applications that don't deal with reading data and updating data. Maybe there are applications that are intermediaries. What if my application is interested in monitoring tweets? I want to know a particular product I'm interested in. I want to know what people are telling about that particular product. Are they saying positive things? Are they saying negative things? Can I use feedback on that product? If I'm a manager of a product and I'm in charge in marketing of the product, that is something I may be interested in. Where is the database in this example? There's a Twitter stream. People will be tweeting 24/7. And there may be tweets at some point about a product. There may not be a tweet about a product at other times. When a tweet happens, I want to listen to the timeline and I want to take some actions. If nothing exciting, I can ignore the tweet. If there's something exciting, I may do the processing and send it to a downstream application to do something about it. So in other words, that is where we are not dealing with the specific CRUD model anymore. Likewise, what if I'm interested in stock data? Maybe I want to purchase this particular stock. I'm waiting for that right price. So I'm triggering an evaluation, and as the stock market is telling me what the price is, I'll keep ignoring the price, but at some point it's hit that sweet spot of the price I'm looking for, and immediately I want to perform a trade, whether a purchase or a sell. So in other words, what if we think of the world we live in as data flow rather than a CRUD operation? So the data flow model says the data flows towards us. At any given time, I want to process the data and I want to take some actions. I could be an intermediary. I may be receiving data from upstream. I may do something with this data, throw it away, transform it, do other operations with it, and then I may send the data downstream. And likewise, it could be transferring all the way through this chain of operations until something could finally take a particular terminal operation or action with it. Well, data flow computing is not new. If you had been around in the 80s programming, you could not have survived the 80s without hearing about data flow computing. Data flow computing was very exciting at that time. We were talking about building data flow machines, for example, and then the concept quietly kind of disappeared. It didn't die away, it was just dormant. but there's a resurgence of data flow right now. But like what we hear and what we do today, we don't tend to reuse the words from the past. It's always fun to give new names for what we already do. So we don't call them data flow today. If I came to you today and said, you can do data flow computing now, you're going to say, old man, we don't really get excited about it. Well, what is data flow? Data flow is where, when input is available for something, that operation can fire, can trigger. It can produce a result and go away. What if I tell you, you can do data flow computing today? You're like, not exciting. What if I tell you, you can program Amazon Lambdas today? You're like, oh my gosh, that's exciting. What is Amazon Lambdas? Data flow engines, right? Because what does it say? If a data is available, I'll fire away, do some work, produce results, and die away. But if I tell you this data flow, you're like, come on, that's boring. If I tell you it's serverless, you're like, oh my gosh, this is amazing. Well, the concepts are resurging. So what I've really noticed in my life is, I've read these ideas about 30 years ago. And I'm like, wow, this seems really exciting. I wish I could program these things. And now I'm at a point in my life where I can actually program stuff I read 30 years ago. This is just amazing. So data flow ideas and all these things are available to us. It's not only commercialization, but affordable availability of these ideas is what really excites me about these things. So it's really about data flow computing all over again. But how do we really program this at an approachable level? So what do we normally do? Well, I could talk about object-oriented programming, but when done, you're going to ask, how in the world do you really code this? Almost any object-oriented language is going to give you the slew of things you can expect. There's going to be something like a class. There's something going to be like an object. So these are the abstractions of object-oriented programming. In a similar way, the abstractions of reactive programming is called observable. There are several different tools available out there. There are so many different implementations. Like I said, in the Java world and JavaScript world, there are many different tools. In the Java world, for example, you have Vertex, you have RxJava, you have Akka, which is a reactive stream library. So there are so many different solutions. Spring itself, Spring 5 is all reactive, and they have a lot of reactive solutions, and flows and monos and so on they are implementing. So this idea is taking a lot of popularity, but one common theme you're going to see is this thing called observable. So what is an observable? An observable is a stream of data. Oh, wait a minute. If that is the stream of data, how is this different from Java 8 streams? So I'm going to say there are some similarities and some key differences. So let's focus on that for a few minutes. So when it comes to Java 8 stream, what does Java 8 stream provide you? Java 8 stream provides you a data flow. It provides you a flow of data, and you can apply various operations on it. You can do filter, you can do map, you can do reduce, you can do other operations on it as well. So you have a stream of data. An observable is a stream of data, just like a stream is a stream of data. They both are data flow. And the similarity ends right there. If you take the Java 8 streams, what happens if one of the methods you call in your filter or map or reduce blows up with a runtime exception? Java 8 handles that with exactly two beautiful words. Those words are good luck. So it doesn't really give you an answer for it. You cannot, because exception is completely contradiction to the concept of functional programming. It doesn't go very well. Java 8 streams doesn't have an answer for you. You have to build it by yourself. Java 8 stream says, good luck, you hope you will design this in a way that makes sense for you. Reactive observables have three channels. The first channel that you get is called the data channel. So the data channel is through which data will flow. And that is the very first thing an observable has, is a data channel. So you open up a data channel and you receive 0 or 1 or 2 or potentially any number of values the observable may provide to you. The second thing that an observable provides for you is called an error channel. An error channel, as you would expect, is through which an error will show up. So as you can see here, an error is treated like it's data. And it's a very, very civilized and respectful way of programming. When something goes wrong, it doesn't throw an exception at you. How insulting and rude that is. Instead, it gives you an error and says, here you go, here's an error for you. And you can receive it with respect and dignity and say, it's okay for things to go wrong. You don't have to throw things at me just because something went wrong, right? How rude that is. And so it gives you an error saying, here you go, something went wrong. And it gives you an error. There's an error channel. Well, notice how clear this is. There's a data channel through which data comes through. There's an error channel through which an error comes through. And then there is the third one, which is called the complete channel. It even tells you that it's complete. There is no more message for you. Whether a data or error, nothing will be coming towards you. This complete channel helps you to perform cleanup operations on your side. This gives you a clear indication the market is closed. I'm not going to give you any more stock data for the day. We're done. So there are three channels that reactive observables have that streams don't. A stream has one channel. Data comes through it. Good luck with errors, and I won't tell you when it's done. Observable says, I am going to tell you, here's the data through the data channel. If something were to go wrong, I'll send you an error through error channel. And as a bonus, I will close the data channel the minute I send you an error. So data comes through data channel. Something goes wrong, it sends you an error and immediately closes the data channel. You'll be getting no more data once there's an error. This goes back to the idea of circuit breakers. If something were to go wrong, it allows you to heal from it. Without circuit breaker, what do? You know something went wrong, but immediately go back and say, can I have data again? That's called programming in desperation. You want systems to heal and take the time to provide that healing, and it says, I won't send you any more data if there was an error. When the minute it sends a complete signal through the complete channel, there'll be no more data or error coming through. Those channels close up as well. So that is one big difference between streams and observable, is that you have these three data channels. How is this different from iterable? Well, iterator. Well, in the case of iterator, you pull the data. In the case of an observable, they push the data to you. So you're in a push mode rather than a pull mode. You just subscribe and you sit there for the data to arrive on your site. And I mentioned about the signal and the respectful dealing of errors. But there is one other big benefit with observables. When you deal with multithreading, when do you normally deal with multithreading in traditional programming? You start programming in sequential way. Why do we start programming in sequential way? Because programming sequentially is easy. So if this is your timeline on your project, you start programming sequentially and you code sequentially until about this time. When you come here, somebody comes to you and says, the performance is not good enough. So what do you now do? You're trying to improve performance and you start throwing in multithreading. When you start throwing in multithreading, what happens? That moment when you introduce multithreading is when your queued code turns into a monster. And the code is unbelievably complex and nobody is able to maintain the code anymore. Not only is your code different, somebody using your code has to change it as well. Because when you introduce multithreading, both the multi-threaded code and the code that uses the multi-threaded code both end up changing. So at this point, you made a lot of people angry. So when you introduce multi-threading for performance, in the end, you made everybody unhappy in the end. Well, what do you learn from this experience? You learn that multi-threading is hard and project goes haywire when you introduce it late in the game. So when you start the next project, you apply those learnings to the next project. So in the next project, what do? When you start with the timeline, you say performance maybe is important, you introduce multi-threading on day one. And by doing so, you start hating the project from the beginning now. Because it becomes unmanageable, unmaintainable, and hard to understand from the beginning, and it becomes a disaster all over again. But what if your code structure is exactly the same, whether you use multi-threading or you don't? We already saw this benefit in Java 8 streams. One of the cool things about Java 8 streams is You have the stream, you can write the stream sequentially, and once the stream works sequentially, hoping that you did the right things, avoiding shared mutability and such, you can come into the stream and you can turn the stream into parallel stream and don't have to change the code structure at all. So we have been beginning to realize that the code structure is exactly the same, whether it is sequential or concurrent, and we haven't had that benefit in a long time. React observables carry that benefit all the way through. In observable, you can write the code sequentially first. What's good about writing it sequentially first? It's easy to understand, easy to work with. We can focus on the problem rather than performance at this point. And when you're done with this, if it serves your purpose and if it serves your performance, you can keep it sequential. If it is not adequate in performance, you can turn on asynchrony and multithreading into it without having to change the code structure. And because you're not changing the code structure, it's easier to introduce late in the game. And you can have the services asynchronous and the clients could be synchronous. Or you can have the services synchronous and the client could be asynchronous. Or you can have both of them synchronous, or you can have both of them asynchronous. You can vary one without having to vary the other. And that gives you a good benefit in terms of improving performance as well. Well, enough talking. Let's see how this all works with a little example. So we're going to take a little example and play with it. But to work on this example, I need help from one volunteer. Somebody who has a smartphone and who can look up something on the smartphone. Who wants to be my helper? Don't be shy. Yes, sir. What's your name?
My name is Nick.
Sorry, say that again.
My name is Nick.
Are you ready, Nick? All right, here we go. Your smartphone is up and ready? Awesome. Thank you for your help. I want you to tell me the stock price for Apple, Google, Microsoft, and Intel.
Would you like to go first?
Any of them. All of them.
Apple is 126.28.
You took all this time to just give me one? I wanted all of them. Faster now.
You can tell all of them in one.
Sorry, you're very slow. Faster, faster, faster.
Apple, Google, yeah.
Yes. Anyone thinks he's slow? Yeah, he himself thinks he's slow.
But it was smart, but I'm not fast.
You're not fast.
Google is 965.59. And Yahoo is 52.58. Yeah, and I get the point.
You demonstrated how the World Wide Web works. Awesome. So let's give him a hand. Thank you. So he demonstrated a few interesting things. I annoyed you with purpose, so I apologize for that. But there's a reason why I annoyed you. Because how does a typical web application work? He demonstrated this really well, by the way. Here's what a typical web application does, right? You make a request. What does the app do? It says, I've got a request now. Let's start a thread. And sits down to work. And it's working. And it's working. So what does the user say? This app is not responding. I'm going to help it. And hits the refresh button. Now what happens? There's a second thread running on the server. When the second thread runs on the server, what does the server do? It's got to spend its resource on both of them. And that's what I did to him. I kept nagging him. I didn't just send the request and be quiet. I'm like, are you done yet? That's a refresh button, right? Are you done yet? He says, I'm slow. You're very slow. Yes, I'm slow. He is not doing his work anymore. He is trying to keep up with my demands. And that's what we do to a server, right? So I was annoying for a good reason in this case. And then what happens? He is working on this, and while he was really keeping up with the request, I kind of kept making gestures, like he's very slow, never mind, give up. And this also happens, right? Because the server is so busy, what does it do? It finishes responses, and the response is, where did the user go? The user went a long time ago. But yet you spend all the time on the job. We do this too. And one small difference, by the way, this is great. He demonstrated how a server works today. We definitely have to rethink about how we do it. But I was doing this talk a little while ago, and I asked the same question, and a guy, Rick, did something very different. No one has done it like this before, and nobody has done it ever since after that. And almost all the time, absolutely they demonstrate like the way Nick did, but Rick did something very different. When I asked this question, Rick was spontaneous. Rick immediately recruited 4 people around him. And he said, hey, you, find the price for Microsoft. Hey, you, find the price for Apple. Hey, you, find the price for Google. By doing so, he demonstrated not only can a machine suck, but a cluster of machines can suck as well. Because you're using all that resource now to not finish your work. And that is amazing how we have been building applications without responsiveness, without ability to cope up with the demands. But imagine you have millions of requests coming towards you, when a lot of requests are going to be, hey, can you have the result now, or I'm not interested, and they leave away. How do you really cope up with that? What if a request comes in with a list of movies you want to watch, but before you could respond, or when you have responded a few movies, the user has left? You can't keep possibly working on the request when the user has already left. You need to be able to respond to it in a different way. So to understand some of these issues, let's look at how we can use observables to do the work. Remember one of the words we talked about earlier, and the word is lazy. You want to be lazy about what you do, and laziness gives us efficiency. So let's look at an example here how we could do this. We got to use a tool, obviously. I'm going to use RxJava here. RxJava was created by Netflix as they realized that they have a streaming problem to deal with, so they wrote this and open sourced it. But you can use a lot of other solutions as well. I mentioned a few already, like Vertex, for example, or Akka solutions. Whatever solution you want to use, the ideas are pretty much the same. Implementations may vary a little bit here and there. So what I want to do here is, I want to say stock server dot GetFeed, and I'm going to pass the symbols to it. So I'm calling a method called GetFeed on a stock server. In this example, I'm going to keep everything in the same JVM, but you can easily go across JVMs using tools like Vertex and other things I mentioned. So in this case, I'm going to create a method called GetFeed. So what does GetFeed provide? Well, the GetFeed is going to be a method, and what this says is, I am going to return to you an observable. That's what it's going to create for you, an observable that you're going to use. So in this case, I'm going to say observable, and observable of stock info that I want to return. Well, that's an observable from RxJava. And what am I going to do? I'm going to say over here, output, let's say created observable. Let's start with that. So I'm creating an observable. But of course, I have to return an observable when it's going to request it. We'll do that in just 1 minute. We'll come back to that and deal with it. Now let's go back to this code. I'm going to store away this observable as a feed, and then I'm going to say over here, output, let's say got observable. Okay, so I can display that I got an observable. Cool. But going back over here, I'm going to take this and say observable dot create, and this uses the same principle as in effective Java. Don't use new to create an object. Instead, use a static constructor. So in this case, what I'm going to do is create this observable, and I'm going to say emitter, and I'm going to go ahead and say emit, and pass the emitter and the symbol to it. Well, that requires the function emit to be implemented. The emit function says output, we'll go ahead and say starting to emit. That's all I'm going to do for now. But notice one thing though. When you go to this sample here, it obtained an observable, but it's not doing anything with the observable. How sad if you just get an observable and it immediately starts working. That's not efficient at all. Efficiency comes from laziness. So it should say, what are you doing with my observable? You're saying, I'm doing nothing. Then smartly it should say, then I will also do nothing. Because you don't want it to efficiently do all the work, eagerly do all the work, only to find out you did nothing with the work you did. So in this case, it also should do nothing. So when you run this code, notice from the output that you get, you see that it says created observable, got observable, but it never actually did starting to emit. It is that lazy. It says, I'll just wait for you to subscribe, and if you never subscribe, I won't do any work with it. In fact, it is really that smart. If I go back here And if I say feed.filter, and I'm going to take the stock info, and I'm going to simply say return true. That's all I did, just as an example. When I run this code right now, let's see what it does. It says created observable and got observable. It is that really smart. It says, aha, but I still noticed you didn't do anything with the data I'm sending you. Why bother doing any work? This is kind of like your boss calls you and says, I've got a project for you, you're going to work on it, and your report is due on April the 15th. And your boss tells you this on January the 15th. When you leave this meeting on Jan 15th, you go back to your desk and you start working on it right away, correct? I know what you're thinking. No, of course not. You promptly will start it on April the 14th because it's due on the next day, isn't it? Well, that is called efficiency. In fact, you know something that the boss doesn't know. You know you are going to quit on April the 5th. Why would you even bother, right? And that is called efficiency. April 15th, aha, I know what is happening. April 5th, I'm quitting. Why bother working on this? That's exactly what this is doing. It says, look, you're not doing anything with the result. Why should I bother? Efficiency. Well, but of course, I want to use the result. So what am I going to do? I'm going to say feed.subscribe. And remember, we talked about having 3 channels. So what are the 3 channels? The data channel, the error channel, and the complete channel. Where are those 3 channels? Well, right here is our data channel. And I'm going to say output the data. Then comes the error channel. And I'm going to say output over here. And we will simply say error colon, and we'll output the error. And finally comes the complete channel, and we will say output done. Well, you could use Java 5 anonymous inner classes if you want to, or you can use lambdas to do this. You can even use method references. So in here, you realize that all that you're doing is just printing it out. So convert that into a method reference, and that's perfectly fine as well. So we have the data channel on line number 14. We have the error channel on line 15, and the complete channel on line number 16. When I run this code, of course, you notice now it says starting to emit. After all, you're doing something with the data. I better start producing some results for you. Let's go ahead and remove these messages right now, and then go back here, and we're going to create the observable, but let's really start emitting. So what am I going to do? Let's say int count is equal to 0, while count is less than, let's say, 3. I'm going to simply say over here, taking the symbols given to us, so I'll say symbols dot stream, then I will say dot map, and in this case I'm going to say, well, stock info, and I will call a method called fetch. Fetch is going to go get me the stock price for that given symbol. Then I say dot for each. Given the stock info, I'm going to say emitter dot on next and pass the stock info to it. So in this case, this is the mouth of the data channel. The on next is the mouth of the data channel. So you're saying, I'm going to start sending data over as I am processing this and send it to the receiver. So this is where you're sending the stock data. As we know, we could use a method reference for this as well, rather than using a lambda, so we can easily change that. That's perfectly fine. So if I go back and run this little code now, what we're going to notice in this case is it starts up and it's pulling the data, and Nick can confirm if those data were correct, and it's pulling the data, as you can see, and giving it to us right here. So that is an example of how we can observe it and get the data that we are observing from the service, and we can display it. So that is the data channel pulling the data. That's the error channel. If there were an error, it will give you the error, and the complete channel to tell you that it's completed. Let's play with this a little bit further. Let's go back over here, and the very end, just for our purpose, I'm going to say emitter dot on next, new stock info, a blah comma 0.0, a little silly example. So in the very end, I'm putting a blah. But if I go back and run this little code now, notice that the data is coming through right there, but when all the data has been displayed, when it hits the end, it sends the blah, and we get the blah in the very end, and you see the display of the blah that gets printed at the very end of this, right there. So you saw the blah. Well, this is a case where our observable doesn't tell us that there is no more data, but it would be nice to be told, because then we know we can take some actions based on that. So for that, what you can do here is you can say emitter right here. So you can say emitter, and what are you going to do for the emitter? Emitter dot on complete. This is the mouth of the complete channel. Well, remember what I mentioned. You transmit the data. The minute you have an error or a complete signal, the data channel will close up, which means that should never go out. I'm not recommending you write code like this, but to illustrate the point, the data channel closes the minute you have an error or a complete signal. So notice the blah is after the on complete. But if you notice here, that's the complete channel's tail end, which is going to receive the complete signal. So when I run this now this time though, you can see the data is coming through, but eventually it's going to hit the complete. And when the minute it completes, it gets the complete signal, and you will not get the data anymore through the data channel because the data channel closes up. So you can see done, but right before the done, there is INTC, and right after done, there is no message. So that's because the data channel was closed. This also gives you an idea. Not only can you receive a complete signal on your end, you can also send an unsubscribe to the observable. So let's say for a minute, I'm a subscriber, and I'm receiving data from you, but at some point I realize I want to perform a trading. I don't want you to be telling me any more data because I'm going to go change to another user story or use case and do some other operation. I can then send you a unsubscribe signal and say, thank you, but no thanks. Don't send me this anymore. And what you can do is you can remove your resources. You don't have to wait for this user requesting data anymore. The user doesn't care anymore about the data. I can let go of my resources for the user at this point. That also contributes to scale and performance also. So how do we unsubscribe? Well, if you want to unsubscribe, you will implement the interface within the subscribe here, and you will call a dispose method on it, and the server will know that you have disposed it and can perform the unsubscribe. So that's something you could do fairly easily if you wanted to. So you can have this communication of subscription and unsubscription on both sides. But what about failure though? Well, you want to be able to handle the failures, but let's introduce a failure and see how we're going to handle the failure. Well, remember what I mentioned earlier. The try-catch is a disaster. We don't want to be dealing with try and catch. Why shouldn't we deal with try and catch? Because in an imperative style of programming, a try-catch makes sense. But in a functional style of programming, which I believe is where reactive programming is an extension to functional programming, it doesn't make sense to do exception handling. I mentioned that it's conflicting rather than collaborating. So you're in a downstream model. When you come to an exception or an error, you want to propagate that as if it's a data. It's just a different data. It's error data. So you want to be able to get that in the error channel. So in this example, what I'm going to do is I'm going to print out error colon and then the error. But where's the error though? Notice this code we just saw a minute ago. I am not touching this code at all. This code is exactly the way it was a minute ago. I'm not going to change anything here. But I'm going to go into the fetch method right here. And within the fetch method, I'm going to do this. If random less than 0.2, throw a very intelligent message. Oops, ran into trouble. Very much like errors we normally get, right? It's like, okay, something went wrong. What went wrong? I don't know, something went wrong. So it tells you that something went wrong. But it's going to blow up. Notice it's an exception. Throw new runtime exception. And where am I doing this? I'm doing this in the fetch method. Where is the fetch being called? In the middle of this pipeline. And right here, I'm doing blow up. Well, you know, Java 8 stream doesn't handle this properly. So what is this going to do? It's going to blow up from the stream. That's going to rupture this stream right here. But good news, we are into an observables right now. The observable says, uh-oh, you failed right here, but this is within the emit. And when you fail that, the observable says, I am going to send you an error signal because I know that I can emit that to you as an error signal. So how does it do that? Well, let's go ahead and run this and see what it's going to do. So when I fire this up, if things go okay, you're going to start getting the data as you did. But when things begin to fail, you see, oops, ran into trouble, but that's an error being printed. So on your side, you just got a notification of the error. The error was given to you like it's a data. You're not dealing with try and catch on your sides. So the errors are handed over to you. You don't have to rely on this. You could easily also call an error. So for example, if I go back here and comment this out, and if I go back over here, I can say emitter dot on error. And you can say new runtime exception, oops, for example. So you could send an error to this as an error object as well. Then of course complete will not happen and the data will not happen either, because the minute there is an error, both the complete channel and the data channel will close up and only the error will go through. And so you can proactively send an error as well through your observable rather than relying on the exception we saw a minute ago. So that is an example of how we can transmit these errors as well. But wait a minute. When you have an error, we saw that this actually terminated. And as a result, you're not getting any more data. So going back to this example, if I uncomment this again, and if I run this now, you can see from the output that you see here, you got the data, but it ran into an error and stopped. This was a little silly example of random error generation. It seems like it's hitting that after the first one, but it's intended to be really random. Okay, there you go. So you can see that it's getting some data, and then eventually it fails. Well, that's a good idea, and also maybe a bad idea. It's built on the idea of circuit breakers. So if something goes wrong, you allow for time to heal. But in this case, if your service failed, there's no point pinging the service right away. You want to wait for it to recover. However, what if you fail on a particular request? In some situations, that's perfectly okay. In other situations, you may have to recover from an alternate source. Like for example, if I'm going to show up to a client site, I look up my map and the map fails. The client is not going to be very happy if I say, I'm not coming to work because the map failed. Okay, why don't you find another map or just ask for directions with somebody else? Well, the good news is you can actually do that fairly well. The way you do that is you say dot on error, resume next. And given an exception throwable, you can say get feed, so stock server dot get feed, and I'm starting in this case a new service itself. But it's up to you what you want to do in these cases. So on error resume next, what does that do? Well, when there is an error, what I'm going to do here is I'm going to print the error. Let's go ahead and say output throwable, and then I'm going to say return the get feed and return that result for me at this point. So what does this do? Well, it's going to have a backup solution to send it to. So as you can see here, the data comes through until the first failure happens. When the first failure happens, it switches over to the second service, and eventually that failed too in this case. But the whole idea is that you can switch over to other services very easily, as you can see with the on error resume next. So that gives an idea about how we deal with errors in the system as it goes through. But this also gives us an idea about something else which is really powerful. And that is, we have this beautiful series of transformations. So in the series of transformation, what we have is, we have a data that flows through, but you could be the intermediary. And this is where some things like a subject comes in. So I could be an intermediary. I could be subscribing to an observable upstream. I could do some work and start being an observable to something downstream. So I could get data, do some work, and push the data. A very powerful model. This is one of the things I really like about the way they have done this. So if I say dot, and I can say filter stock info over here, stock info dot value is greater than 100. Well, notice a minute ago we had prices like 146, 965, and 71. But now I'm saying I only want prices over 100 and nothing else. Well then, if I run this now, you can see that we are getting the price for Apple, we are getting the price for Google, we're not getting the price for Intel and Microsoft because those are less than $100. So you can do filtering. You can also do a couple of other things. For example, you could say perform a map or transformation. Given a price, you can say return new stock info, the stock info dot ticker, but the stock info dot value times 1.1. I can modify the value along the way also. So as you can see, the bloated values are being given now, and you can transform those values along the way. Much like that, you could perform a filter, you could perform a map, and several other operations. Well, the filter itself is kind of like a valve, a little flap. It can let data go through and occasionally block some data. So it can decide whether the data should go through or block it, like a little flap. On the other hand, think of a skip and a take as switches. So if I say take, I can say take, let's say 4. A take 4 will allow 4 values to go through, and the minute the 4th value goes through, it will turn off the switch and no data will go out. So as a result, if you notice here, when I run this, you can see it says Apple, Google, Microsoft, and Intel, but it says done. Aha! Notice what just happened in this case. In this case, the take is going to monitor how many data you're getting. At that point, it sends you a signal that it's complete and sends upstream an unsubscribe message as well. You can do a take for a particular count, or you can say take while given a stock info.value is greater than 100. The minute you see a price less than 100, stop sending me data. I want to switch over and do something else. And you can do that as well, and that's a take while. Likewise, you can use a skip and a skip while as well. Skip will eliminate data that comes your way and only give you data after it has skipped that many values. Skip while is more logical than count based, and you can use that. Well, this gives us an idea how we can use these things, but there is one unanswered question. In all these examples you saw so far, what we have here is one observable and one subscriber. What if I have multiple subscribers? How is that going to work? Well, here comes the charm. You can have a source of data, but you can have any number of subscribers. For example, there could be a source that is telling you a location of a flight. You could have multiple observers on it, multiple subscribers. One may be interested in monitoring the flight to arrange ground crew. Another service may be interested in monitoring the same exact flight, but to arrange for maybe fueling. A third service may be interested in arranging for next departure crew, depending on the delay of this flight, what have you. So I could have multiple observers, multiple subscribers to a same observable. But the question is, do all these subscribers see the same view, or do they see a different view? Here's an example. Let's say I'm in a chat session. I'm chatting with a friend of mine. We are having a conversation. When I'm chatting, one of my family members comes online at that time. I'm the same person. I'm going to be chatting with two people now. But in this particular case, it's two different sessions. My session with my friend is different from my session with my family. And I'm going to maintain the two sessions, but those two different conversations, I'll keep the context in my mind, and I'm two different conversations even though I'm the same observable. Or there's a situation where I'm chatting with my wife, one of my children may come online, I might rope them in, and we may be as part of one conversation, all the 3 or 4 of us. And in this case, I'm still the one observable, but I maintain one session with all the subscribers, which are my family members. So it really depends on what the context is. These have special names for them. If I maintain multiple sessions, I'm known as a cold observable. If I maintain one session for all the observables, all the subscribers, then I'm called as a hot observable. So multiple sessions is cold, one session is hot. And so how do you do this? To understand this, let's take a little example and play with it. I'll come up with an example which is a lot easier to work with. So in this case, what I'm going to do is I'm going to create an observable dot interval. That's a lot easier. The interval is going to emit a data at every given interval. So in this case, I'm going to have an initial delay of 1,000, and then I'm going to give a period of 1,000 time unit dot seconds. So every second, I'm going to emit a data. So in this case, of course, I'm going to put a thread dot sleep, let's say 50 seconds, so that it actually runs through it for a while. Okay, so that's basically what I have so far. Now what am I going to do with this? I'm going to store this away as observable. So I have an observable on my hand. So let me say observable dot subscribe, and in this case, I'm going to provide a sample. We'll call it as print1. So a print1 is a method I'm going to go ahead and implement. So that's my method I'm going to implement on this one. Let's actually fix this, dot subscribe. And this method, subscribe, is going to take a sample, and let's go ahead and say print1. So what am I going to do in the print1 method? Let's take a print1 method. So public static void print1, and print1 says I'm going to take a long value, and it's simply going to say output s1 colon plus value. So let's start with this real quick and see how this works. So when I run this, you notice that at every second interval, it is going to fire up a message in the interval, and you're going to, it should have, and then we're going to print it out. So in this case, of course, I'm going to come to the print1 and print s1 and then the value in this. So that's basically what my observable is going to provide for me. I'm not sure why that didn't do it. We'll figure out. So let's kill this for a second and come back and take a look at it. So this is going to bring the data, and when the data arrives, which is the value, I'm just asking it to print it out. Does anyone see the error here? So what did I do? Oh, did I say? Oh, sorry, yes, 1 second, not 1,000 seconds. I'm sleeping. Thank you. It was doing what, code always does what you type, not what you meant, right? So, absolutely, thank you. It looked great, yeah. Awesome, yeah. So, right there you can see, we can see the display coming through every second, as you can see right there. Okay, so that's working, but let's go ahead and say in here, not only do we want to do that, but we want to also put another subscriber to it. So what are we going to do? Let's ask it to say thread.sleep for 5 seconds. Okay, set for 5 seconds. Now I'm going to say observable dot subscribe sample right here, and let's call this as print2. So I have a little print2 that's coming in, and you can imagine what I'm going to do in print2. All I'm going to do is simply say here is print2, and all I will do here in print2 is print S2 and the value. Well, the question now is, of course, whether what it's going to do with this exact same observable. Well, this observable says, I am going to route this request to the print2 that's coming in, and here is the print2, which is going to print S2 and the value back to us. What's the consequence of this? Well, the consequence of this is, let's see why it is not finding the function. So this is going to be, subscribe, not where did that come from? There we go, thank you. So what is going to happen in this case? 5 seconds later, it is going to kick in the second subscriber. By default, your observable is a cold observable. So you have 2 sessions here. And as a result, this is going to kick in a new evaluation. Let's look at it slightly differently with the other example. If you look at the stock server, what's going to happen here is, when you do a new subscription, it is going to fire up this as a separate session. I don't know if you recollect this, but if you remember, I initially did not call subscribe. And when I didn't call subscribe, even though we created an observable, it never really called the emit. Emit was called when you called subscribe, not otherwise. That's exactly what's going to happen. It's going to call emit for the first subscribe, then call emit again for the second subscribe. In other words, this lambda is exercised for every subscription. That's exactly what's going to happen with this interval. In this interval, it's going to ask it to start synthesizing or generating the data for every single subscribe that comes in. So when you run this code this time, notice that in this case, S1 started, a good 5 seconds goes by, S2 kicks in, and you can see that they are in a lag. They're not in the same level. So this is like, you could be watching a video on YouTube, a friend of yours calls you and says, what are you doing? You're into the 15th minute, but then you say, I'm watching this video on YouTube. They go to YouTube, they start in minute 1, not in minute 15. Their session is different from your session, even though you both are watching the same thing on YouTube. But what if I do want to share? Well, it depends on the application, right? So if I do want to share the same thing, I can still do the same, that also. So to do this, let's go ahead and terminate this and retry this. And notice how simple this one is. All I'm going to do is go to this one and say dot share. So the dot share creates yet another observable. Notice that observable is the same thing as we had a minute ago. I could have stored it into a variable. I can have a tree structure. This could be a cold observable. The share could create a new joint shared session. If you subscribe here, you'll be in a joint session. If you subscribe here, you'll have a new session. So we could create a tree structure of these as well. And that is one of the nice, beautiful hierarchies of this. And in this case, if I store away observable, I can create another shared observable separately from it by calling share. But with that one change we made, when we run this code this time, S1 is at 0, 1, 2. At the 5th second, we bring on S2. And notice those two are in sync with each other because they are seeing a shared session at this point. So we can implement some of these ideas very nicely without much effort at all doing this. And that brings up one other concern. What if our performance is becoming a concern? Well, the first thing is, it's possible that your source is generating data very quickly, much faster than your subscriber is able to handle it. Keep in mind, this discussion only makes sense when there is a period of real high frequency and a period of normal frequency. If you're going to be always slow, and that is going to be always fast, it doesn't really make any sense dealing with what are called back pressures. So what's a back pressure? A back pressure is when a system starts firing data at you, if you're keeping up with the change, that's with the arrival of data, that's good. But what if you are a little slow occasionally? Imagine for a minute that I have a system where I'm going to look at cars that are driving by, take an image of the license plate, and I'm going to check for their details, registration details. Imagine I have a really good high throughput, and I'm able to look at this automobile and immediately find out, and I'm able to keep up the pace at which the cars are flowing through. But imagine there's one little suspicious car called Venkat's car going through. And the minute you see this car, you immediately trigger a request, and your local system says, dude is unknown. Now you want to go look at other systems and find out, and that's taking a little bit more time for you. What do you want to do with all the other cars that come afterwards? One answer is, forget them. Let them go, just process this. And that's perfectly fine in some scenarios. Depends on the application. In some systems, you want to deal with only the latest data. You don't care about the data that was there before. Imagine you are tracking a flight. You are doing some work. Now you want to go catch up the flight's current data, maybe, not where it has been. In other situations, you might be interested in processing all of them, even though you may take a little longer to process this. So what do you do about it? In short, what we want to do is we want to deal with back pressures. How do you deal with back pressure? Well, the idea of back pressure is pretty common, but when RxJava was being developed, they released initial versions, as they should, without implementing back pressure. And so observables did not have back pressure implemented. So when you look at this here, you can say, things related to back pressure were not available on, well, they were available on observables, but unfortunately, when they came to implement back pressure, they realized it doesn't work really well. And they realized they have to come up with slightly different implementations for supporting back pressure. And they had a choice to change everything they have to change to support it. But then they realized if back pressure is not needed, you can implement in one way. And if back pressure is needed, you can implement it in a slightly different way. So what they did when RxJava was released as a newer version, RX2, what they did was they quietly removed back pressures from observables. So the recommendation today is, if you don't want back pressure, simply use observable. If you want back pressure, then use what is called flowable. What does a flowable do? I'll call this as observable 2. And in this, what you can do is, you can say dot on back pressure buffer, for example. So you don't want back pressure, use observable. You want back pressure, look at flowable. So what does flowable do here? On back pressure buffer, meaning, well, I'm getting data at a faster rate than I can handle, start buffering it. And I will catch up with it at some point. Or you can say, on back pressure drop. You know what? I don't care. I'm handling something. When I'm busy, if more data comes through, just drop it. And whenever I'm done with it, I'll process the rest of the data. Keep in mind, there is no one right answer. It depends on your application. Imagine for a minute, I have an app where I'm going to be typing. As I'm typing, you want to take action, like the search assist. Well, guess what? It depends on who is typing. Somebody could be really good at typing, and they could type stuff, and you want to take action on it. My wife always tells me, I am superb in typing, backspaces, that is. So when I type, I keep hitting the backspace more than actually typing stuff. If you're going to have a tool that's going to see my typing and respond, you're going to burn up a lot of resources. So what do you do in that case? Well, what you could do is, you could ask it to throttle. A throttling says, this dude is really bad in typing. His name is called Venkat. So when Venkat starts typing, start throttling it. So all the garbage he types and hits the back spaces, when he takes a breather, now process what he typed, not otherwise. So there are these kinds of things available already to decide what you want to do, and you can debounce, if the frequency is very, very high, you can say, I'm going to just take the signals only during a certain interval of time because it's too noisy for me to handle it. Once again, keep in mind, there is no one good answer. So they gave you all the answers, so you can pick the one that makes sense for your application based on what you want to do. But keep in mind, these solutions work really well only when there is a period of high activity and then there's a period of normal activity, right? If you're going to be in a high activity a lot of times, a buffer wouldn't make really much sense at all because you're going to overflow the buffer and you're done. What do you do after that? It doesn't make much sense. So what do you do if you are going to have very high period of activity for an extended period of time? One thing you can do is bring in asynchrony. So to bring in asynchrony, what you could do is you can delegate operations to yet another thread. How do I delegate operations to another thread? Well, one of the problems we deal with often is when you want to deal with asynchrony, your code structure changes and becomes a total mess to deal with, and that's not fun at all. Well, the good news is the code structure is exactly the same whether you are synchronous or asynchronous. So to understand this, let's go back to our stock server.getFeed for the symbols. Let's do a filter, and in this case we'll say stock info.value is greater than 100, and then we will say .map. Well, actually, let's just do a map alone. We'll do a map, and then we will call a method called transform, and we will pass to this the stock info. And once the transform returns it, we'll do .subscribe, and in this case we will say output the data. So we'll say system.out println. Well, okay so far, but what about the transform method? Let's take a look at this transform method. So public static, this is going to return a stock info, and the method is called transform, and it takes a stock info, so we'll send a stock info, and in this case, of course, I'm going to say return. So this is going to return new stock. You know what? I'll just return the stock info I got. So that's all I'm going to do, just get it and return it. Let's go ahead and run this and see what it's doing. So you can see the price for Apple, Google, stuff like that coming through. Great. What thread is running this? So to understand this, let's go over here. Oh, let's do one more thing. Let's change this to print it. How about that? So what does print it do? It's going to just print it. So let's go ahead and say here is our public static. Let's say this is going to be printed, and this takes a stock info, and all it's doing is output stock info. So again, let's make sure the code is working, then we'll come back and change it a little bit. So right there, so what are we going to do next? Well, in this case, I want to know what thread is running this. So output, we'll call it transform, and we will say thread.current thread, and I'm going to print that information. Likewise, I'll print it here in the print it. So here's my print it. There should be no surprise. You're in a main thread, everything should be working in the main thread. So you run this, your transform is in main thread, your print is in main thread, no surprise at all, as you can see. So everything is running in the main thread. But what if I want to run them in a different thread altogether? Well, one thing you could do in this case is put them in a different thread. So thread.sleep, let's give it a little time to sleep. Let's now go here and say .subscribe on. When you call subscribe on, you are asking it to change the thread that's going to run your stream of data. Well, where do I ask it to run? You can create your own pool and execute a service pool. If you create your own pool, you can say executors dot, let's say executors dot, executor service dot new fixed threaded pool, right? Oops, sorry. So executors new fixed thread pool, let's say a pool of 10. Well, that's your executors. And I'm going to save that away as executors. And what am I going to do with this executors? Well, with this executors, what I can do is I can try to save that away into a variable and say schedulers.from, and I can specify the executor service. Now you are saying run this in that particular thread, and you can delegate it to a thread to run it on, that pool rather. And this will run it in that pool. In fact, let's take a look at it and see if it does. So in this case, I'm going to simply say at the very end of this, executor service dot shut down, and we will shut it down. So when I run this now, you can see that it's running this in the pool thread, as you can see. Well, that's one way. Alternately, what you could do is you can say, all right, I want to run it in a separate thread, but I don't want to be creating my own executor service. Well, what do you want to do then? Well, I want to be able to run in a pool that you provide for me. And you can say, in this case, schedulers.computation. Computation will create a pool of thread, the number of threads in the pool equal to the number of cores that you have. It assumes that your task is computation intensive. It creates as many threads as the number of cores that you have on your machine. Or you can say .io. It creates a pool. If the threads are busy, it'll create more threads, because when you have I/O intensive threads, you can have more threads in your pool than the number of cores. When you have computation intensive, you don't want to do that. Performance will suck if you do. So it gives you the ability to transform that, as you can see. So when I run this, you notice those now are running in a separate scheduler thread behind the scenes. One quick note about subscribe on versus something called observe on. This is a little, I'm not too happy with the wording here. Subscribe on puts the entire stream in a separate thread, whatever pool you set. Think of observe on as stage gates. When you say observe on, what is before the observe on will be in a separate thread pool. What's after observe on will be in a separate pool. Subscribe on doesn't do that. So subscribe on is like parallel in Java 8 streams. It doesn't matter where you put parallel in Java 8 stream, the entire stream will be parallel. That's how subscribe on works. Observe on uses stage gate. When you put observe on, everything before it will behave differently. And whatever you tell on observe on will affect downstream. So you could have multiple observe ons. It doesn't make sense to have multiple subscribe on. So that way you can control the threading of different parts as you wish. So that's basically about how you can modify the threading and work with it. So where does this take us? This is becoming very pervasive. There are two places where you would make use of these. The first place is when you're designing your own libraries, your own APIs, you might consider you want to make them reactive. The other place is if you're using Spring, if you're using a lot of database APIs today, like MongoDB, for example, as one example, or if you're using Angular 2 or Angular 4, you are dealing with reactiveness already. These libraries and frameworks and platforms and tools have started providing reactive libraries. So in a way, there's no escape. You may or may not provide reactiveness to your own APIs, but you cannot escape the reactiveness of the libraries and tools that you're going to start depending on. So that becomes very relevant to be able to do that. So one of the real benefits of this is to really focus on making the application responsive, application reactive, and to revisit the four things to make the application respond to these things, to respond to actions. And the goal is to be using message-driven systems, provide elasticity, provide resilience, and also to be able to provide responsiveness when building applications. It is a level of abstraction. It's a paradigm shift in a way. Over the period of time, you see paradigm shifts along the way. I've probably seen about 3, if not 4 paradigm shifts in my life so far, and it's pretty rewarding to see these changes come through. I would say the most difficult for me has been paradigm shifts. Learning a library is easy, learning a syntax is easy, but paradigm shifts usually take a lot more effort. This is a paradigm shift that's been a little bit easier for me, only because I came through the functional programming already, and having gone through functional programming, and relating to this as a next logical step to functional programming, really helped me. Until I drew that connection, I was a little apprehensive about it, a little frustrated, because I was trying to see where does this make sense. But and then I realized I've been learning about two things kind of concurrently, and then I realized that they're not that far apart after all. It's really one is like a logical step from the other one. That became a lot more easier in my mind to then focus on. Hope that was useful. Thank you.